Jamil Mazzawi has over 32 years of experience in the semiconductor and EDA industries, holding engineering, sales, and management roles at companies including Vericity, Rambus, Sun Microsystems, and Jasper Design Automation. Now at Optima, he has a strong track record in developing and promoting advanced verification and automotive technologies, and is the author of over a dozen related patents.
Hi everyone. So I'm going to talk about the emerging challenges and solutions for functional safety and security for automotive, AI, data center, and space chips. The presentation will be high-level overview, mostly of the challenges, what needs to be done, and what kind of things we are trying to solve. My background is mostly in verification, both SpecMan, just Vericity, if you know, and Jasper, doing formal verification. But now the focus, I think, in the new front, which is safety and security, that's my focus. So in safety and security, the relevant segments, mostly automotive is the most important segment. So any automotive chip need to comply with both safety and security standard. Also AI chips, especially if they used in cars, data centers, and space. We're going to discuss a little bit about the relevant standard, what is the fault modeling required, what's the common safety mechanisms used to protect against faults of the chips, and what kind of EDA challenges we need to verify, and we're going to touch a little bit about what Optima is doing to solve these challenges, and if you need more information about what Optima does, our route is just the exit from this talk. So multiple chip segments needs safety and security. Automotive definitely is the main driver for safety. The standard here is called ISO 26262. Data center, they less have a standard, but they have requirement mostly to detect and resolve soft errors. Also, some companies are dealing with in-system monitoring. How do I make sure that chip is still functioning well and there is no damage to the chip while it's being reduced? Meeting fit rate compliance, how do I ensure uptime, and so on. If we talk about space chips, chips going outer space, so outer space soft errors become a much more prominent problem. So in space, also soft error detection and recognition. Industrial chips like robots and so on, they need to comply with the standard ICE 61508. On the right-hand side, the security domain. In many chips today, we have secure assets, secret assets inside the chips, like encryption key. And we need to protect these assets. So the standard for automotive is ISO 21434. Other segments that also need to comply with different standards, and they have the security requirement, smart card chips, gaming chips, space chips, and so on. So I'm covering two topics, safety and security. So while functional safety, I can talk about it for hours. I'm going to try to cover it in maybe 1 or 2, 3 slides. So what is functional safety? And first, we need to understand that after the chip is manufactured and it tested on the tester, it is guaranteed that it doesn't have any fault and it's all working well. Now we put it inside the car and it is participating in the driving of the car. We can think about Mobileye, for example. It's mostly passive or active ADAS, but a lot of autonomous driving, full autonomous driving is happening now. So these chips are part of the driving mechanism. Now what happens if one transistor out of the billion transistors inside the chip stops working? This can be a transistor that is not very important, main function of the car, but it can be a transistor that decides to turn on or off the braking system, or now all the image or radar that we are working on is doing bad stuff. So again, the chip is working, it's driving the car, and now suddenly one transistor stops working. Most challenge. It is transient fault, which means that the flip-flop is working, it has the value of 0, and now suddenly, because of a nuclear particle will come from the sun, radiation from the sun, this nuclear particle hitting the chip and hitting certain flop, and now the flop change value from 0 to 1 or 1 to 0. So it's called transient because it doesn't impact the chip itself. If you reset, everything works well. But at this moment, the chip is not in the state that it is supposed to be. Now, this single flop that flipped, what is the impact of this on the system? Will it crash the car? Or will it shut down the data center? Or it will just correct itself and be fixed and so on. So these are the main challenges. What happened to the chip during when hardware happened and what happened to the chip software. So functional safety is about prevention, detection, and correction. So I either need to prevent faults from happening. I can do this, for example, with hardening, with better circuit technology, wider transistors, and so on. Or I can detect it. Detection is good in automotive, for example, is good enough because if you detect a fault happens, you can report up the system to the higher level system and say I have malfunction. Now we can either disable this function, let's say the radar, and we continue using the camera, or we can disable automatic braking and so on. So if you detect a fault, you can declare that this chip or this unit or this subunit in that chip is malfunctioning. You can disable it and maybe continue. You need to go to replace the chip in the garage, but that's a different problem. So detection is very important. Prevention is good, and also you can do correction. If you think about CRC, for example, or parity, CRC and ECC, they can correct. They can tell you you have one bit was detected and it was corrected, don't worry about it. So what is all these things that they detect, correct, or prevent are called safety mechanisms. Safety mechanisms, they are ensuring safety. So safety mechanism examples are parity, CRC, and ECC. This is the most common method that we use this even outside of automotive. In automotive, we use also DCLS, dual core lock step, which means we duplicate a certain unit twice, like we have two CPUs and they are working in lockstep. They get the same input. We compare the output to make sure that they're always compatible. If a fault happens in one of them, then we know that something is wrong, so we can detect it. Or we can do TMR, triple modular redundancy. So 3 modules are instantiated. So we are paying 3 times silicon. And this can also correct, not only detect, because if there is a problem in one, the 2 will vote out the other. We can also TMR at the flip-flop level. We have 3 flip-flops that if one of them is wrong, the 2 are giving me the right answer. STL, I'm not sure if anybody here is involved in STL development. STL is a very common safety mechanism. It is software test library. It is software-based safety mechanism. It is a software that is running on the CPU, performing some kind of self-test. It's reading and writing to registers to making sure that the system is still intact and there are no problems with the chip. If a fault is detected, if incorrect behavior is detected, then there is a fault, and we can declare that this CPU has a problem. SLT is system level test. It is similar to the STL, but it's used more in DataCenter. It is longer, takes long time, and cover more things than STL. Test pattern is also very common, and I will show a few slides about it. It's used mostly in data transformation and design. So I'm going to illustrate 3 examples of 3 safety mechanisms: data pattern, STL, and fifth level selective hardening. So the first example is data pattern. Data pattern, maybe I better show you the diagram. Let's say that you have image processing. So that image processing or any kind of data transformation. You can think about AI also. AI chips, you give them some data and you expect some data out. So the idea here is that we create certain images or certain frames that we send them to this image processing. We know the expected results, And so while the chip is working, data in is coming from here. At some point we stop and we send data from certain buffer here. We send the data to the processing unit, and then the data that comes out here, we check it. If it is matching what we expect, then everything is good. Otherwise, we say fault is detected. So the CPU sometimes is used to program the data that we send in and what we expect, and so on. So you can look at this here. If this is your waveform, time is progressing to the right, of course, and the functional window here, and then we stop, we send test data 1, it is tested, we know if there is fault or not, fault detected or not, and then we continue with our functional mode, send another frame, and so on. So it is interrupting the regular operation of the chip or of this unit to test it to make sure that image processing unit is working correctly. The same thing can be done for AI, for example. So let's say that I've implemented this mechanism that we showed in this diagram, and I did simulation, and it is working. So now start the safety verification part. So safety verification is additional task. So sometimes I feel that verification engineers are all the time getting new challenges, new tasks, and so on. So that's another one that we need to do. So functional safety verification is about measuring how many of the possible faults these three images can find. So imagine if I have my image processor has 1 million gates. So every gate can have stack at 1 and stack at 0. So I have 2 million possible faults. I'm sending 3 images. The question is how many of the 2 million faults these 3 images can catch. So, and once I find this, is this number, let's say I got 80%, is it meeting my requirement? Maybe I have a requirement of 90% or 95 or 99%. Does this, it's called DC or diagnostic coverage, does this diagnostic coverage meet my requirement? If not, I need to do something. If yes, then I'm done with the verification task. So the challenges that we see, and of course we don't solve this, is the fault simulation time can be very, very low. Imagine we said 2 million possible faults, so we are doing the same simulation that you've done with your VCS or with the CEO. Now we need to repeat it 2 million times. So this can take 2 million times more if you do it with normal simulator than your regular simulation. So fault simulation can be very long, and we need Optima provide technology to shorten this thing. How do I automate the process? Because I don't want to sit and wait for 2 million faults. I want something automated that tell me, okay, you have this kind of coverage. Here are undetected faults. These gates are detected, these are undetected. So a lot of automation is needed that Optima is providing. How do I know? How do I improve my frame? I send 3 frames. Let's say I have a requirement. I can maximum do 3 or 4 frames. How can I change my frames to meet the goals? Or how can I add one more frame that give me the highest coverage? That's also a challenge that we cover in our technology. Another interesting challenge is sometimes, always, we have configuration bits that control certain features in the RTL. And some logic is not relevant to the task of image processing. Maybe you have certain mode that is not supported in the main task, and so on. So also we have technology to isolate the parts that you don't care about and put them and mark them as safe, and so on. And how do I shorten my number of frames? Another example of very common safety mechanism is called STL, as I mentioned, software test library. Again, it is diagnostic software. It is doing read-write operation to the register. It can be written in C or assembler. So we write some software, we compile it, and then we simulate how this software will do. So the first time we write this version, and we run it with simulation on the chip or the CPU. And then we need to measure what is the coverage of this. How many of the possible faults again, let's say 2 million faults, how many of these faults we can catch, how many are not catch, and how can I improve, change my software? Maybe I need to change here and use T5, not T0, so that I can catch more and more faults. So the same challenges as before. It's about fault simulation time. How do I reduce the fault simulation time? How do I debug undetected faults? And how do I improve my STL to meet the requirements? So the goal from functional safety for STL is I need to reach certain DC, let's say 90%. I want to reduce the length of the STL because the STL is the same as in the image data pattern. We are stopping the CPU from performing its normal task, operation task, to be its testing. So we cannot stop it for 50% of the time. We need to reduce the length of STL so that it can fit within the scope. That's also a technology that Optima has to reduce the STL. The process is that we write version 1 of the STL, we perform fault simulation using the Optima tool, examine the results, then we move the STL to detect more faults and repeat until reaching the goal, then we go on and again the fault simulation. The challenges here are fault simulation time can be very long and it can really be very long. How do I automate the process? How do I know how do I build my STL based on my results? And how do I deal with unused parts? And how do I shorten the STL? The next challenge is different. It's about, now we talked about hard error, now we're talking about soft errors. So, as I mentioned a little bit before, the soft error can hit the flip-flop and change the value. Now, the impact of this single flip-flop that got hit can be catastrophic or can be nothing, because there is a phenomenon that will research and explore in the industry called logical masking. Many faults that happen on the flip-flop will just disappear. After one cycle, maybe 2 cycles, maybe 10 cycles, many faults will disappear because the hardware has this kind of self-healing, we can call it phenomena. We can talk about it if you want. But there is phenomena this exists, that many faults will disappear and they will go away later on. Now, the question is, how do I know out of the 1 million flops that I have in my chip, which ones are faults on them will disappear, which ones these faults will be corrected by other safety mechanism, and which one can cause catastrophic behavior. This is a dedicated tool that we have for this that can analyze the soft error impact for all your flops. It has a very fast fault simulator. You can do millions of fault simulations in a few hours to give you an answer, and then we give you a ranking for every flip-flop. What is, it's called AVF, what is the criticality of this flop? You need to protect it or not. This is very relevant in automotive, also relevant in space, as I mentioned, and very relevant in data center, switches, and so on. In the security domain, security has lots of challenges. One I'm going to talk about here is the fault injection side channel attack. As you may know, a fault injection attack is when the hackers take the chip from the market, buy a car, maybe take the chip out, and take it to the lab and inject faults on the chip. And they're hoping it's like, you shake the Coca-Cola machine, maybe something will go out. It's the same thing. They put laser on it, they do EM radiation on it. You have here the picture of this laser attack. And their goal is to hit certain flops. They don't know which flops they want to hit because there are many flops they don't know about yet. But they want to hit flops that maybe to open the gates and will allow data to leak. So the attack is about causing fault injection using laser, EM, electromagnetic or clock glitching, and power glitching. So this is the fault injection, and then to find the results, they look at side channel. They look at the output and they compare differences to find this. difference and maybe extract information about the secret asset inside the chip. The main technology that is used by most customers today in this market is to verify how good is my defense mechanism, because you need to implement defense mechanism to prevent data leakage. Once implemented, how good is it? The main mechanism is sending post-silicon, sending the chip to the labs, like the picture here, and then the lab people will attack it and tell you data leaked or not. And then it is very hard to know what happened, which flip-flop they hit those data to leak. You just know that data leaked and the data is not, the provided feedback is not very good. Plus it's post-silicon, everybody knows what is post-silicon fixing bug in post-silicon mean. So what Optima is offering in this domain here is we have a tool that imitate or simulate fault attack using laser and EM, that you can do all the verification of this pre-silicon with high visibility of what is happening. We inject faults similar to what a laser would do. So we can bit flip multiple flops and see what happens, tell you if data leaked or not, and if data leaked, will tell you which flops we need to protect to prevent this. So this is the Optima Safety Platform. We have dedicated a flow for STL, data pattern, software security, and many other common safety mechanisms in the market. It features ultra-fast fault analysis and fault simulation engines. It's used now by multiple customers in 8 countries. Certified by 2 companies to be used in Automotive, Tufo, and SGS. So fault analysis is not fault simulation. Fault simulation is just one step in fault analysis. Optima, we provide one tool that allow you to do all the fault analysis steps, from static analysis, maybe a little bit similar to what was presented before, the static coverage maximizer, concept analysis, fault simulation, dynamic coverage maximizer, and fault feedback engine. So all these steps are in one binary, in one software. We all use a unified fault database to handle this. Other competitors will give you multiple tools to achieve the same thing. So the integration here is very important. All the engines run very, very fast to allow you to converge on those quickly. This is the common cycle that happens in functional safety, that you give our software the RTL or gate level, a workload of a quality simulation, we analyze it, we give you results, you look at the results, do some debug, improve the RTL or the workload, and run it. And you do this a few times to reach the goal. And we're solving a lot of automation